Thank you. Good morning, everybody. It's actually quite surprising to see so many faces already on the lecture number 6 or 7. I'm very glad that. Okay, so last time we take an attempt to derive the nonlinear sequence model, and we almost succeeded. It was just the last step which was given as a homework. But since I already gave you the answer, I will not check if you do it again. So nonlinear sigma model, just to refresh your memory, and my memory as well. I will repeat the main steps how this theory is derived. So, first step, we write the action for kernels, the original action, S, which depends on the harmonic series phi, and this action is minus I, phi dagger, and then in brackets we have everything we should have in the denominator for the ring function, epsilon minus psi of p plus e of r plus omega over 2 lambda and plus I 0 times phi. Lambda, to mind, is a matrix with 1 and minus 1 for retarded and advanced functions, and phi is the Grassmann field with 2n components, where n is the number of replicas. 2n components, 2n Grassmann components. So this is the original point. We will take the limit n to 0 is very end of our calculation. So then what we did with this action, we first average over the disorder. Disorder is this V of r here. And this average over disorder, so the first step, disorder average. Which generates, it removes this V of r, and instead it generates some term with action which is of the fourth order in the phi field. So we have now an interacting action. Different replicas interact with each other. So it's not a real interaction, it's just looks like interaction. It's the result of averaging. The next step, once we have this product of 4 or 5 fields, we want to have back a Gaussian action, which is quadratic. So the next step is Hubbard's topology transformation. Hubbard's topology transformation, it introduces the new field, which did not exist before. Introduces the matrix Q, which is Hermitian, and it has the same size as the phi field, 2n times 2n. It's a matrix. And we will have, after this transformation, we have an action which is quadratic in phi, quadratic in q, and there is also an interaction q interacts with phi. So the next step, once again, was to integrate out the phi fields. Integrate over phi. It's just a Gaussian integral which introduces the determinants, puts the logarithm matrix of the exponents to write the determinant. And then finally, the next step was the saddle point approximation, where we just take the minimum of the action. We found that saddle point is equivalent. We just reproduced the equation for self-consistent Born approximation for the original result. And this way we more or less include all the non-crossing diagrams, which is self-consistent Born is the same as non-crossing. It's taken into account non-crossing diagrams. And moreover, it turned out that this saddle point approximation is not just a single point where this action is minimized, it's a manifold. It's a manifold, and when this Q matrix is restricted to this manifold, we can represent it. Q matrix is represented as T vector lambda T, where matrix T is just unitary of the same size. T belongs to the group G, which is unitary group of size 2n. And Q matrix is invariant whenever we, so for each matrix T, for each unitary matrix, we can construct a Q matrix with this formula. But it turns out that for different matrices T, it can end up with the same matrix T. So there is some redundancy. You can have different matrices T, they all produce the same matrix Q, so matrix Q actually belongs to what is called closed space. This group G should be divided by the group A of matrices that commute with lambda. A is the group of matrices that commute with lambda to n times n. These are log diagonal matrices. It's like lambda, like this. We have one unitary matrix for the double plot and the other for the retarded and the other one for advanced. So the Q matrix belongs to this interesting thing, which is called the closed space, or in my case it will be the signal manifold. And this whole manifold, all matrices Q of this form, with some constant T, they all minimize the action. So the last step that we should have done is gradient expansion. Action is minimized if T is constant, and that action also is when frequency is 0. Now we expand with small frequency and with small gradients of Q, and we get some action which is not constant, which is a functional. So this gradient expansion is where we stopped. And I will now do this expansion on the board, and you will see how the result comes about. Yes, please.
What does this space mean with the division? I'm not familiar with any operation that can divide two spaces.
Divided. Okay. So, do you know what U is? This U is this.
Is a matrix with those space rotations?
Well, actually, U of n is any unitary matrix of size n. Just n by n matrix, which is unitary. Unitary means U labor U equals 1. So it's the inverse is the same as Hermitian conjugation. And this is actually a group. The group is the set of objects with where you define the operation of multiplication. So you can multiply two matrices, two unitary matrices, and you get a third unitary matrix. This is a group. This is a group, and this is a subgroup. We have a matrix of size 2n, all possible matrices of size 2n, and as a particular case of this matrix, there are also matrices of the form that this way. This is the group which is like this. It's matrix 2R. to A. So imagine you have a matrix like this, which is zeros here, and something unitary in the retarded set, and something unitary in the fast. So structure is unitary now. This is also a unitary matrix as a whole, and this the space of such matrices I call UM times UM, because it is a direct product of two unitary matrices. Product of something, I don't know. So this matrix commutes with lambda, just because you can multiply diagonal blocks separately, you are commutes with 1, and A commutes with -1. Now, if you take some matrix T, which is this size, and you say Q equals T dagger lambda T, this is a Q matrix. Now you take a different, so T is a big unitary matrix without zeros here. Now if you take another matrix T, let me call this matrix K. Now instead of T, I will take T times K from the left. I will say this is new matrix T. Old matrix T, now it's a new matrix T. Now I ask, what is the new matrix Q? New matrix Q is new matrix T, that is lambda, and then it's new matrix T. And it's just the same equation. So this T dagger, K dagger, lambda, A, T. Matrix T is just T. But K commutes with lambda, I construct K like this. So I can commute it to lambda, and then K dagger K is 1. Such that this thing equals just T dagger lambda T, which is just the old matrix Q. So what I show here is that there are different matrices T that lead to the same matrix Q. It's like for any matrix, for any unitary matrix of size to n, you can construct a matrix Q. You have a big set of all unitary matrices, but you should identify those of them that differ only by multiplication by the matrix K. So when you identify this, like an equivalence class in the group, when you identify these matrices within the class and now say that you distinguish only different classes but not matrices inside them, it's the same as to say that you distinguish different Q matrices but not different T matrices. This is called factorization of group by this equivalence relation. But actually, since it's not a proper subgroup, when you divide like this, what you get is not a group itself. So Q matrix, you cannot multiply two Q matrices together. Another Q matrix. That's why it's called the closed space, or just people usually say manifold. Manifold is a very general object. So.
This division is just a sign to this concept.
Sorry?
This division is.
This division means it's a division in the set theory sense. So you have a set of objects, and then you have an equivalence relation on the set. So you go from the set to the set of equivalence classes. You can divide by any equivalence relation if you want to mathematically reduce statement. So actually, this division means that any matrices from U to N which differ only by multiplication by some matrix from here are identical, and in this ratio they are considered as a single element. It's just it's not like you divide 10 by 5. You divide this. Is it clear here? Yeah.
But I have questions. Are all matrices complete with lambda?
Sorry?
All matrices complete with lambda.
Not all.
So if I do it, are they always of this form K, or there's other matrices out of this form that also complete with lambda?
No, all matrices that commute are of this form. Okay, if this points there, later I will discuss many states like this, and we will have even the explicit matrix forms for such things, so you will see how it works. And also, I should have mentioned from the last lecture that this sigma model that we derive, and this space that, this set of two matrices that we have is actually, as a name, it's a sigma model of the unitary symmetry class, so just unitary class. Unitary class. There are other versions which have other spaces here and they have other names, and this we will discuss soon. But unitary class is the simplest option, and this is what we are left with. Yeah, just another example so that you can understand what closed space is. It's important, and actually I'm not, as I said, I'm not a mathematician, so I can say anything, and I don't take responsibility. But just for you to understand, what the Q matrix is actually the matrix lambda that was rotated by this Q rotation. Just a simple example, imagine you could have a unit vector, which points in some direction. And then you apply the rotations to this vector. So rotations are orthogonal matrices, which rotate the three-dimensional space. You apply, so this is vector n, and then you apply the orthogonal matrix and the 4 times n. This will produce a new vector n. So, question. Well, let me say that the original one was not n, was z vector, the unit vector in z direction. Then you rotate it, and what you get is all possible unit vectors. Any unit vector can be represented as z vector rotated by some orthogonal matrix. Now the question for any orthogonal matrix, this orthogonal matrix is the element of the group S3 group of rotations, three-dimensional space. So it's orthogonal matrices of size 3 and with determinant 1. Question. For any orthogonal matrix, you will get some vector n here. Vice versa. How many of these vectors n you have? Infinite. That's a good answer. How many matrices of this form do you have? This group SO3, actually, it can be parameterized by Euler angles. The angles means that the dimension of this group, dimension, equals 3, not 3 parameters in set. And what is the dimension? How many parameters define the vector n? 2. Yeah, it's just a unit vector. It lives on the sphere. So the dimension here is 2. Now you please tell me how does it happen? Why is it different? For any matrix, here I can have a vector n.
Because you can rotate unit vector around each axis.
Yeah, exactly. So if I have two orthogonal matrices that say O1 and O2 that are not the same matrix, they differ. O1 is equal to O2 times, say, R, the matrix that rotates around z axis. It's also rotation. So if I put this O here, it will first rotate around z axis, and this vector will not change. And then the matrix O2 will rotate itself. So it means that two different orthogonal matrices, if they differ only by z rotation, actually produce the same vector n. And these are z rotations around the axis z. They form also the orthogonal group, but only of size 2. 1 is 2. It's rotations of two-dimensional space, the space perpendicular to the z axis. That's why this vector n actually belongs to the closed space SO3 divided by SO2. This is exactly the same construction, and you know what this space is. It's called a sphere. And sphere is not a group. You cannot multiply two n vectors to get a third n vector. You can do it with matrices. You have a group of matrices of size 3, you have a subgroup of matrices of smaller size 2, which rotate around, so you can factorize. And what you get is not a group anymore, it's a closed space. And in this case, this closed space is just simple sphere with a sphere in the middle. No?
The topological sense.
This is a sphere. Well, actually, it is a two-dimensional sphere. It is two, because they are multi-dimensions. And this is some generalization of this notion. It's a construction is exactly the same. You have some matrix lambda, you rotate it with a matrix T, but there is a subgroup of matrices that cannot really move it. Therefore, you have to factor out, and then what you get is not a group anymore. It's some also some. How to say? It's a generalized sphere. This is a sphere in this metric space, and it's not two-dimensional. And square dimensional, but 2n squared, to be precise. But the construction is the same, so the logic is. Okay. Is it more clear now or less? So let's, I will express this was before, I didn't plan it. That's why I raised it. So let's proceed, and the point where we stopped yesterday, was this gradient expansion, and it was the action S of Q that has the following strange form. It was minus trace of the logarithm of an operator, and the operator was epsilon minus psi of p plus I lambda over 2 tau, and then there were some small corrections to this thing, and the small corrections also on the page. Yeah. Was plus omega over 2 t lambda t integral. It's not a Q matrix. It's t integral one corner. And another one was minus I v Fermi, vector, Fermi velocity, times. Because what I have written here is different. Gradient T times T delta. Oh, sorry, times T delta.
For some reason I have plus.
For some reason you have plus I Fermi, T gradient, right?
Yes. Yes.
This is the same.
Yes. Exactly.
If you take
Yes.
if you take the difference of these two objects, this is the difference, you will have. See how we did it in elementary school. If you want to compute the difference, you get minus I v Fermi, and then gradient T dagger plus T gradient T dagger. So this thing in the brackets is just the gradient of T dagger, and T dagger is 1. And the gradient is 0. So it's actually the same. So I will write it this way, just because I prefer to apply only one operator to an object, and here you have T, which is both the derivative and gradients of the two operations. Yeah, so this is the action after we took the saddle point, and we wanted to expand it in these two parts here, which was called A and B. Yeah, this was A, this was B. This is the trace of the logarithm. And this object in front was called the inverse green function. Because this is exactly what the green function has in the denominator. This inverse green function is just a matrix with inverse retarded function here and with the inverse advanced function. So to cloud it, it's just plus minus. Yeah.
There's somewhere there's supposed to be a term which is just trace of Q squared, right? Because it's substructure, if you just
Yes, as soon as we took the single point, it is weird.
Okay.
Okay, so what I have here is logarithm. I just rewrite it once again. It's minus trace log of G inverse plus A plus B. A and B are small. I would like to expand with small A and B. That's why I write it once again like this. Minus trace logarithm of G inverse. I just neglect A and B. This is the zero order approximation. Minus trace log 1 plus G A plus B. Or GA plus GB. When you have a sum of two logarithms, it's the same as the logarithm of the product. So if you multiply G inverse times here, you have G plus A plus B. And now this first term here, trace of log of G inverse, this G inverse is just a constant. It doesn't have the Q matrix inside, it doesn't have T matrix inside, it's a number. And this number is the same in every replica. It also does not depend on replica. Number is just one, it's the same one in every replica. Therefore, this trace here is actually proportional with right side. So this no, it's not correct. Not that.
Yeah. Oh, sorry. So it was correct.
It's like alpha,
It should be like that.
just a little bit.
It should be like gamma.
It's proportional to the number of replicas. Because each replica contributes the same number. You sum this node G is a number and trace sums of all replicas. So you have n times the same number, and since sometime in the future we will get limit n equals to 0, we can just disregard this term. It's a constant which is added to your action. So we all know from classical mechanics that action, if you add a constant, nothing changes. All the equations of motion are the same, and moreover, this constant is 0 in the replica limit, so it's completely irrelevant. And we need to expand this logarithm of 1 plus something small. And I expand it, so it's my this trace minus GA minus GB plus 1/2 GB squared. I expand to the linear logarithm A and linear quadratic logarithm B. Now, why do I expand to the quadratic logarithm B? Because B, this operator, has the vector inside, it's Fermi velocity. It's a velocity which is on the Fermi surface. And this trace involves also integration over all momenta, which means integration over the whole Fermi surface. So when I will integrate this B, here it will be just zero. That's why I need the next one. Okay, so point number 1, this first one, GA. It's very simple. It's only of 2 G lambda together minus trace GA equals wait. Sorry. Before I do this, I should tell you what G is. G. So G is the following thing. G is the matrix. Epsilon minus psi plus I lambda over 2 tau inverse. knows how to invert the matrix. The G endorses this. There is a very powerful trick when you want to invert the matrix. It goes like this. Well, I will write the answer, and then it will become clear that it's correct. It's epsilon minus psi minus I number over 2 tau divided by epsilon minus psi squared minus 1 over 4 tau squared. Actually, I multiply this object with this object, the sign for now is negative, and I get the difference of two squares. Square of this minus the square of this. Square of lambda is 1. Square of the first one.
Why minus?
Good point. Was it's minus, but there is I inside. Yeah. Or you can do it like this, you can write separately the retarded and the constant and invert them separately, but then you should also keep track of what values actually A and B you have. So this is G. It is now a number in the denominator and some matrix in the numerator. So point number 1 minus trace GA, this first term here is minus integral over all momenta, which I immediately write as the integral over variable psi. Repeat using the linear times. And then G times A. Doesn't have trace here. Now tracing. We already have momentum integration, so this trace will be just a trace of the matrix. The replica and the space, omega over 2, T, lambda, T, dagger, and then this epsilon minus psi plus lambda over tau, divided by epsilon minus psi squared plus 1 over 4 T squared.
Right plus
Sorry?
right plus.
So this is an integration over sine of psi squared in the denominator. Well, first of all, since I am using a board and I can erase, I will simplify using this object. I will simplify integral. We integrate over psi, so epsilon times the same as psi. We can flip the sign of psi and then shift the epsilon. So I will just replace this new by psi. It's a change. It's a very simple change of variable. Shift and flip. So we have this integration of sine of psi squared in the denominator, and we have a linear object in the numerator. So this first term is odd. It changes sign, and psi changes sign. That's why I will erase the cascade. This is what we are left with. It's a simple sign of this problem. This I hope you know how to do. Okay, minus omega 2 minus I over 2 tau, right? And it's small, so I have to write 2. T lambda, T dagger lambda, this case is here, trace T lambda, T dagger lambda. And what is left is the integral of this cycle, this denominator, which is what?
Oh.
It's just pi. It is pi times tau. Yeah.
Can I ask a question? T depends on position, on R. So T is the variable in the space.
Yes.
Is it okay?
Yes, that's a good question. So T depends on the point in space, but T is very slow. It changes on some large scale. And this momentum here, the integral actually converges on the scale of the infinite particles.
Okay.
reinforcements. And we exactly are using this inequality that mean-free path is short, momentum q is large, so momentum q is small, the scale at which t changes is large, and therefore we can just compute it out and forget. So at this point we forget that t depends on r, because this is like, this kernel is very small in space in the sense of the mean-free path. Okay, so what will happen if I multiply all these terms here? Minus I tau cancels out. Check what's wrong. Let me check the correct thing.
It was like it was minus.
It should be I pi mu over q. Pi mu omega. So pi is there, mu and omega is there. Pi is here, mu is here, omega is here, I is here, plus is here, tau cancels. I have just some extra factor of 2 which should not be there.
It's because of the integral. It's because of the integral.
Yeah. Trick me. So I tricked you. Yeah, of course, super tau, and the result is this. And now the trace here, as I told you, t down the t dagger is not a Q matrix because t stayed in the wrong order. But under the trace now, I can take this t and put it in the last position. And now this is the Q matrix. Now this t dagger down the t is the Q matrix. So what I get is trace minus times Q. This is a very important thing. So during this calculation, I have separate matrices T and T dagger, but in the end, everything combined into a matrix Q. And the action that this trace log I origin, sorry, it is not written here, it was last time. So trace of log which I expand in gradients originally also contains just the Q matrix inside. So doing this expansion, I used some explicit parameterization, did things, but in the end, I get my matrix Q back, which is very nice. If it doesn't work, it means there is some mistake in the calculation. So now the second part is this term, 1/2 g times b squared raise 1/2 raise g times b squared is, and this is tricky. So b is written over the rest. I d firmly greater than t. Very nice. So it's 1/2 integral over all momenta, which is just integral over psi. And then I will write it this way. Since I know in advance that I can shift the variable and make it like this, I will have psi squared plus 1 over 4 tau squared on the first green function, and in up there I will have psi minus I lambda over 2 tau, right? So this is the green function 101. Then I will multiply it with b. B is I d Fermi gradient t dagger. And then I will, so I have a square, so I should not put another thing like this again, psi minus I lambda over 2 tau, I d Fermi gradient t dagger. And I will have another denominator. Size squared plus 1 over 4,000. It's just a product. And there is, of course, trace the matrix. Now, look, we have a denominator which is an even function of psi, doesn't depend on the sign, and in the numerator we have one odd function which changes sign here and the other one here. So,
you probably also missed now integration of an angle of the favorite surface.
probably. That's a good point, yeah. So this is the integration of psi over the absolute value of momentum, and there is also the value v here, as I advertised, which points in any direction, and I have to average over the Fermi surface. So V Fermi times V Fermi averaged over the Fermi surface will be 1/2 V Fermi squared divided by the dimension of the space. I times I is mass. What I have now is trace. Well, okay, I can also take out nu. Nu is just a number. Trace integral over psi. In the denominator, I have psi squared plus 1 over 4 tau squared twice squared. And from the numerator, I either should take this psi times this psi, or this term times this term. In other words, if I take only the even product to cancel, so what I have is psi squared times gradient t dagger squared. This is psi times psi. And from the product of these two terms, I have minus psi over 2 tau plus minus 1 over 4 tau squared lambda gradient t dagger squared. Please somebody tell me what this is. Yeah.
Okay. So here you are assuming a specific dispersion or not?
No. I just assume that it's isotropic. That's what this means. Isotropic,
Yeah.
the Fermi surface is a sphere, but I only need the Fermi velocities of how this dispersion behaves near the Fermi energy.
Yeah.
And actually, you can do exactly the same thing for any dispersion, just instead of listing, you will have some Fermi squared average over the Fermi surface. Okay, so
Second part is 0.
which part is 0?
The second part.
This one.
Yeah, because the whole is the second part of whole.
This is a positive function. Integral and
That falls in both.
it's just all the second order.
plane.
Oh, yeah. Well, since this was your homework, I assume that you all know what these integrals are already. And what I have here is just the final result. It's minus pi nu V Fermi squared tau divided by 2 times d. These are all these factors and also the tau which comes from the integration. And then it's a trace of gradient t dagger squared minus lambda gradient t dagger squared. Actually, these two things give the same. Psi squared and 1 over the tau squared, they give the same number. And this number is taken out, and we have just 1 minus that. Yeah.
And you just omit the brackets or the parentheses for the gradient, right?
You mean here? So yeah, gradient is only on the t, which is very dense. Too many letters. Okay, so as I advertised here, it's very nice that we have our Q matrix back in action. So this strange function of t, we should now express in terms of q. The q is this one. T is this one. And it's not originally obvious that it can be done, because, as I explained in the beginning, when you know the Q matrix, you don't know the G matrix. There are many different G matrices for the same Q. So if you have some expression in terms of T, it is not guaranteed that you can write it in terms of Q. But this particular expression, since you did the whole calculation correctly, unfortunately, we were not the first ones to do that still. This whole expression can be written in terms of the Q matrix. And moreover, I can also write the prefactor in terms of the diffusion constant. The diffusion constant is V Fermi squared times tau divided by D is the diffusion constant. Nu is here, 2 is here, pi is here, so pi nu D over 2 is just this fraction. Sorry. This should be over 4. And what we have here is the trace of the gradient of u squared. So gradient of u squared actually equals to this bracket here, up to factor of 2. Does anybody believe or not? Actually, you don't have to. I will prove it right now. So it's much easier to go the other way. Starting from gradient, trace of gradient of q, and dividing this expression, you just take q, you substitute this here, and you apply this number to either t derivative t inside q in all possible ways, and you get this trace gradient q squared equals trace. What is gradient of q? It's t dagger lambda gradient of t. I can act with my gradient in the second. Second factor here, all on the first gradient t dagger plus gradient t dagger lambda t squared. This is how you take the derivative of the product. I have 1 for that. Now this gradient of t dagger, I don't like it because I have all gradient acting on t, not on here. So this gradient of t dagger actually equals minus t dagger, gradient of t dagger. This is how we differentiate the inverse 1 over x. Yeah? T dagger is like 1 over t. This is how we, actually it's the same statement we had previously. We had this V fermented. You can act with the gradient on t or t dagger because they were equal, so it's due to the same thing. Equals. Let's do something. Here, let's multiply the whole bracket by the matrix T from the left and by the matrix T dagger from the right. Tens to it. Under the trace, it's like cyclic thing, so it's T cancels against the T dagger. Yeah?
I have a question regarding the trace in the action. So it's like the integral of the momentum and the usual trace of the matrix. But
yes,
when you integrate the momentum, you add that dimension, right? It's additional. So it's like size of the dimension of the space. So it's now like not dimensionless action, although action has to be dimensionless or
it will be dimensionless just, well, actually it's a real space, and T and Q actually depend on the point of space. So what we have here is a median of the integral in R, and then there is dimensions. Okay, so just to continue here, I put T and dagger from the left and right, and I have trace of something squared. The first term is the T dagger cancel. lambda gradient t, lambda gradient t, and t dagger from right. Now this second term, t cancels t dagger from here, it's minus gradient t, t dagger, lambda, and these two cancel. So it's minus gradient t, t dagger, lambda. Actually, it's a commutation. It's the square of the commutator. Last step just expands this square. We have the square of the first term plus the square of the second term. They are actually the same. If you multiply this, if you square this, or if you square this under the trace, you can move lambda from back to forth. So it's trace lambda gradient t to dagger squared 2 times. 2 times because it's the square of this, it's the square of this. And then there is minus 2 times the product, first by the second. Yeah? Everybody knows how to find. And the product of the first times the second lambda cancels out, it's just gradient t to dagger squared. And compare it to this thing and you see it's the same object. Even the sign is correct, so it was minus, it's plus. And this extra 2, this 4, you from here, so this is like that.
So do I understand correctly that we actually assume that q or t dependence on r is very, very slow, so when dragging it out of the integral, we just can think only about zero harmonics, and this is exactly what zero temperature.
I'm not really sure what you mean by zero.
I mean, this is Fourier transform of basically, it's omega equals to 0.
Yeah, we just assume that locally it has some constant value, but at some very distant point it has some different.
Yes.
So we don't do a Fourier transform.
Yeah, I understand that, just meant that.
We do a Wigner transform.
Okay, but in the beginning we had only one integral over dp, and
But
now
it was a trace of the matrix, so actually you have two momenta inside if you wish to, which you feel equal when you take the trace. And then we do the Wigner transform of it's P and R integral. And
yes.
P integral and R integral.
Okay.
This is too much more. Okay, so we are done. This is our first term. We just prove that it's correct. This is the other term, which for some reason has integral of R. Therefore, I will write the result here because it is very, very, very important. The action of the nonlinear sigma model is the following. I mu over 4 integral over the whole space trace of two terms. T gradient q squared minus plus 2 I omega lambda times q. End of the story. With a plus, we have pluses. Pi mu over 4, 2 I omega, pi mu over 4 degraded. Yes.
What is the integration of R?
Well, actually, it was always there, and I just discussed it. Previous question. So we assume that T is different in different points in space, but it changes very slowly, and the momentum integral that we have here converges very fast. It converges at the scale of the mean free path. Therefore, within this momentum integration, we assume that T is constant. And we can integrate on the side, assuming T is constant. But once we integrate it on the side, we still have integration of the whole space because T is different in different forces. This whole trace, when we write the integral, it also contains the argument. If you like, the dp, the argument in the presentation, I really wouldn't like to go into this technical detail. If you wish, we did this whole calculation for some small piece of our method, where T is something, gradient T is something, then we repeat it for all other pieces, and then we add it all together, and it gives us the real space integral. And as was also pointed out, we need this space integration just because the action should be dimensionless. Otherwise, it will have dimension of the first one.
So this was a approximation of the original model yesterday. So what's the small parameter again?
So this last step was gradient expansion, and the small parameter is that this omega tau small, and that QA is smaller. Q is the typical momentum for the Q matrix. So the gradients should be small on the scale of the integral.
Are you saying that the integral of a space is something that traces
GA. Yes, this is a full trace which is traces the metric space, traces the operator space. This operator has two momentums. So to take a trace, what we do, we actually do a linear transform. We go to the real space representation with respect to the sum of this moment, but not with respect to the difference. And then this trace becomes the integral of P times the integral of R. So we do Fourier transform in one way. And this sine integral is the integration of P, and this left is the integration of R.
and we don't write the integral over R?
Sorry?
Why don't we write the integral over R?
Even here, right? Because we are lazy. It should be written everywhere.
So it's not a conversion. I see.
You know, this thing is so slow, so weakly depends on position R that we don't have to bother with this integration up to the very end. But you're right. So if we do it rigorously, there should be R integration in every formula. Yeah.
Are you sure that you wrote the right 2 before the omega?
This is what I have in my notes.
Okay. So, but independent of spin.
There's no spin for the very first equation. It's for spinless electrons. This observation was to spinless electrons, and use the density of states also without taking into account any spin. If you do have spin, you still do the same and then multiply the result by 2 because spin is the conserved quantity. Consider that scattering depends on spin. Of course, there is another version where you have some spin over coupling of ferromagnetism, where spin is involved, and then it's slightly different.
I'm just asking about 2 factors.
The factor of 2 is, I'm sure it is correct, 99%. And we will see that it is indeed correct just in the next 10 minutes.
Okay.
Yeah?
Maybe stupid question. This can maybe all be represented by finite diagrams.
Of course,
How does it?
it was discussed on the first.
Oh, sorry. I missed that one. Good.
But I can repeat it for you personally.
Because I try to see the finite diagrams.
Okay, so this is a major milestone. We were going to this formula from the beginning of our course actually, and just once again this action looks simple. It has the quadratic term and the linear term. What can be simpler than this? Still, this is a non-linear sigma model, which is highly non-trivial, and this non-triviality lies in the fact that Q is not just any matrix. It's a matrix that is restricted to lie on this closed space. or which is the matrix. For example, you can easily see that the square of Q is just 1, the square of L is 1. So it's like a sphere, as I said. The sphere was with a vector, this is like a sphere with a unit matrix. Unit means something squares of 1. And even the simple, it's like simple mechanics. You have kinetic term and potential term. Kinetic energy, potential energy. But you live on the curved space. The sphere is curved. This manifold, this cosine space is curved. Therefore, it's like a simple mechanics, but the one that is studied by general relativity in the curved space. So our effective theory for the Q matrix is like a relativistic mechanics. But truly relativistic, not this special relativity, general relativity. Okay, so what should I say? This is a nonlinear theory that has parameters, diffusion constant, omega inside, and of course we cannot solve it exactly because it's non-linear and all these other things. So we will apply some approximation in order to solve this, and the first approximation which comes to mind is the perturbation theory. This, so if there are no questions at this point, I don't have questions. This is the toughest part of this. Yeah.
Say again, why we can't solve it exactly? Because Q existence is with space and waiting for the space of Q to be hard.
Sorry, what will the hard? No, we took the several points.
Oh, you mean we can solve it directly, like overall, not this, not this.
I did not understand the question. Yeah, we have.
Can you compute the partition function for this test of Q?
Exactly.
Yes.
I can't. Because it's non-linear. So I could do it if Q was a free field which has all components independent. But since Q has some non-linear constraints, I cannot do this. Well, so this we will not need anymore.
Sorry, may I ask two questions? First, Q square equals to 1, and how we can see it, just from the fact that it lies on U to n divided by the fact that Q square equals to 1, it is the fact that Q is lies in U to n divided by U n.
Q square equals to 1 follows from the fact that Q has this form. And from the same fact,
yes,
follows that Q belongs to this.
Okay, and the second question, our actual small parameter is t, right?
No, t is dimension.
Sorry. I mean that why can we actually suppose that only q with small omegas would be relevant?
Because we studied final diagrams the first two lectures.
Okay.
Which were especially singular for small q and omega.
Yes, I mean, looking at this specific action, can we see it somehow directly? Because I see the diffusion constant and...
we will see it in 5 minutes, or even in 4 minutes. So, just for this general expression, this is something to be remembered. Q is t tethered lambda t belongs to U of 2n divided by n. So this one is defined on such a curved space, and we have to solve it. And we cannot do it exactly. We can do a perturbation theory. Well, what is the parameter of perturbation theory? Which we will resolve. This action has a minimum. There is somewhere a minimum of action. It's on this manifold, and when gradients in omega are 0, it's just constant, the same constant on the manifold. Now, if I do have a finite it's a potential energy. It tells me that some points of the manifold are better, some points are worse. And there is now one point that this thing is minimum, and so perturbation theory. Perturbation theory. We now say that our degenerate manifold, when we consider finite frequency, actually it selects one point of the manifold where the action is minimum, and this point is q 0 equals lambda, which is lambda itself. It's like a potential energy, here lambda equals q. Look, trace lambda minus q squared equals what? Trace lambda squared plus trace q squared minus twice trace lambda. Well, this is a simple algebraic exercise. Lambda squared is 1, is a unit matrix. Q squared is 1, is a unit matrix. These are constants. Then actually this is 2 times trace of unit matrix. It's constant. This. So this trace lambda q, which we have here, is actually the same as having trace lambda minus q squared. So it's like a potential energy, like an oscillator, quadratic potential that tries to bring q to lambda. There is one strange thing here that we have passed, which imagine it, but we don't get. Let's say we are working with much smaller representation for imaginary frequency, then it will be a real potential which will really drive to lambda. So lambda is the minimum of the action, not of the sigma model action, minimum. And if we deviate from this point, our action will grow. So perturbation theory is an expansion in these deviations near the minimum. Now, what's the parameter for this expansion? How do we know that this only the vicinity of this minimum is lambda, and actually only this parameter? If omega is not too small, this works. As omega gets smaller and smaller, the perturbation theory becomes worse and worse. So for this perturbation theory, omega has a dimension, and that's why I will not say how big or how small it is. Omega, let's say just omega, not too small. If omega is not too small, then the potential is a parabola which has a minimum, attracts to that minimum, and we can do perturbative expansion. How do we do perturbative expansion? We have our Q matrix equal to T dagger lambda T. At the minimum, Q equals lambda and T equals 1 unit. Well, we can take other values for T, just unit is easier. Well, T is unit, Q. Now we want to expand near this minimum, so we say that we should write T as a T, I just remind you, is the unitary method for size 12. And there is a very simple mathematical statement that if you take the exponent of what? Of I, no, exponent of W over T, I just want to replace the matrix T with the matrix W. T is the exponent of W. T is unitary. This means that W is anti-emission, minus W delta. Whenever W is anti-emission, the exponent of it is unitary. And why I want to represent T like this? Because T equals 1 corresponds to W equals 0. So I will say that this exponential now is 1 plus W over 2 plus W squared over 8 and so on. I can just expand in small w, and this will be an expansion of t near the very one. W is small. This is our preservation. When omega is big, W is small.
Why we want it to be anti-condition? What's considered?
So that t is unitary.
Ah.
And moreover, if I expand just the linear order W, I can now write a Q matrix. Q matrix is t dagger value t is exponent of minus W divided 2 lambda exponent of W divided 2. I have just used the capital W difference minus W. And if I expand now the Q matrix in terms of W, what I have is the first one is lambda, both exponents are 1. And now I have W either from here or from here, so the next one is plus 1/2 commutator lambda of W and so on. So my Q matrix is meaning equals lambda, and then W tell me how I deviate from this minimum, but only the commutator enters here. Once again, there are many matrices W that are different, but have the same commutator of lambda. If you add to this W a matrix that commutes with lambda, this thing will not change. Let's add to matrix W something that commutes with lambda. So what I'm trying to say is that this W anti-Hermitian has many elements, but we don't need all of these elements. We need some small amount because there is a redundancy. It's the same redundancy we have here. So we need full W to parameterize the full unitary group. We need a smaller W to parameterize the cosset space. So we apply another restriction. We assume that W anti-conduce with lambda. Lambda W does not mean lambda is 0. We can always do this just based on the linear order. If we want, we can always add something that commutes with lambda to fulfill this identity.
If the order is high, then we cannot apply this.
Well, actually, it works in all orders. I just demonstrated in the first one because it's easy. So, and actually, then, if lambda W is the same as W lambda, this term can be rewritten as lambda times W. So this complicated one is lambda. Yeah.
Yeah, so like initially we have function integral over U, now we will have function integral over W, and what's the Jacobian of this information?
It's written here. Well, actually, it's not written here. But we will discuss it. It's written here, discuss the Jacobian.
Another question. Why do we actually need all this? Why couldn't we just say that t equals to 1 plus something small and that's it?
Q equals 1. Or T equals 1.
T.
T. T is a unitary matrix. If you take 1 plus something small, it's not unitary.
Ah, so this is just a way to fixate.
This is a way to do it.
Okay.
So with this W, we always remain within the unitary group.
Yeah. Okay.
It's like a rotation. The W is the generator of the rotation, the exponent is the rotation matrix. We can expand to any orders, it will be still a rotation matrix. And if you are interested in the linear order, yes, you can just write one as W.
Ah, okay. So, but
And
in
if
the
you
next
want to
one.
go to other higher orders, you will need this explanation.
Okay, thanks.
Okay, so what I'm saying is that if T is exponent and W is some small matrix with these restrictions, you can actually, let me write it differently now. So exponent times lambda times exponent, W anti-commutes with lambda, so it's just lambda times the exponent of W. It's an additional requirement I impose on W because I have a freedom, because I don't need all unitary matrices, I need only those that generate the process space. So I deliberately chose W to obey this relation because it's convenient. And one convenience is immediately since lambda anticommutes with W, I take W, changes sign with the exponents, combine with a single exponent of a single W, and now you understand why I put myself here. Also, for simple. And if I expand this W still small, so I can now do the expansion of this plus W squared in 2, also. And now expand it into the second one. And since I have W anti-Hermitian, anti-commutative of lambda, I can also explicitly represent it as the following matrix: B minus B diagonal. This is the matrix that it anti-commutes of lambda because it's anti-diagonal. Lambda is 1 minus 1, so it's like this. If I have 0 here, two matrices here, they always anti-commute of lambda, and now the condition that W is minus W integral just relates these two blocks. So with this W, I automatically fulfill these identities. Now, if I put this W into this Q and then I put this Q into that action, what should I get? It's very easy. Gradient of Q is lambda gradient of W. Gradient of 1 is 0. Then it is gradient of W, and this one I repeated. Lambda gradient 1. Trace gradient of U squared equals trace lambda gradient of W squared. You see, I expand only to the second order of W. The action to the second order, which means that gradient of Q I need only to the first order because it's squared. W anticommutes with lambda, meaning this is minus trace just gradient of W squared. And using this form of W, squaring it, taking trace, get 2 trace gradient D dagger gradient. Good correct? Yeah. That's correct. And the last term, trace lambda Q with omega. It's even easier. The first one is a constant, which I don't need. Trace of lambda squared. So what I do, I put this form of Q here. Then it's trace of 1 plus W plus W squared of lambda cancels out. Trace of 1 is a constant, which I don't care of. Trace of W is 0 because it is 0 on the diagonal. And trace of W squared is the only thing which remains. And it is minus, so it cancels out, minus trace integral D. Right? So if I put all these things in my action, this is the action. I will get an expansion of the action near the minimum, near the square lambda. So this perturbation theory is now the action in terms of W, which looks like pi nu over 2 into R trace D. So gradient Q squared is 2 times this trace, 2 by gradient N, so gradient D squared gradient D, so B there plus 2I omega, where this minus and 2I already cancelled, minus I omega E whatever E and the story. Now it's a Gaussian action because B is an unrestricted matrix. I will take into account all this curvature of the space by using this exponential here, expanding, and W has some restrictions which were resolved, so it has no restrictions, and I have a Gaussian theory quadratic action for the field B. Now, B is a matrix of the size n by n, it's twice smaller. N by n matrix, and there is just complex numbers, it doesn't have any restrictions. And this is the action for B. Is it clear? It's approximate, it's not exactly the same action, it's just an expansion. I took only the leading terms. There are further terms here which we will discuss later. But this is the leading part. And if there are no objections to this formula, this is exactly the proof I was asked about the coefficient plus 2i omega. I forgot who asked this question. Oh, he's right here. Yeah, so the proof is that what we have here is exactly d q squared minus I omega. Exactly the thing that we have in the denominator for the diffuser. You see, the relation between this coefficient and this coefficient is correct exactly because we reproduce the standard propagator of diffusion. Yes.
But the reason no longer cross variables.
Grassmann variables were fine,
And
but the
this is
matrix Q was already not equal. Q was shifted by M, which was pi squared, so it was already reproducing. The Grassmann variables disappeared a long time ago.
Yes, I see.
So, once again, this action, unfortunately, is ended up on the bottom of the board. That's why I have to continue here. So this action tells us that our field B describes the deviation from the minimum of action from Q equal to lambda. And since Q equals lambda is the minimum ground quadratic terms, there are no linear term of the deviation. With a quadratic term, and this quadratic term gives us the Gaussian action, and we can compute what is called propagator. The average B star I J B K L. Matrix elements of B, this is a Gaussian action, that's why there is only the second order average, and we can take any matrix element of B, we can compute its correlation with any other matrix elements of B with the star. But I don't want to do this because actually the correlation is only they are uncorrelated. So each element is correlated only with its own conjugate. And this can be seen as this trace and bit everything. I just don't want to write it exclusively in elements. But anyway, this thing is just the inverse of the quadratic form matrix that we have here. It's 2 over pi inverse. Wait, sorry, no, let me write this. Okay, then I will get delta I k, delta j, and divided by dq squared minus I omega. It's the correlator at the momentum q. So you can compute this correlated in real space and then do the Fourier transform of the momentum space. And this is exactly the diffuser. Up to some different prefactor here, but this, what is important is this denominator. Yeah.
What is the physical meaning of this correlator? So it's like some auxiliary field, not initial field phi.
This is an auxiliary field B, which is a matrix field.
Yeah.
I have no idea what this field is. I just introduced it to Howard's Polish transformation. Yes?
Yeah, exactly.
But I have computed the correlator, so I can draw a diagram. And B is a matrix, which means it has 2 indices, I and J. I and J. B star. B, the other one, has 2 indices, K and alpha, which turn out to be equal. I equals to K, J equals to L, so it's given I, J. And the propagator of B If it will be just a simple field, it will be a simple line. But since it's a matrix of two indices, it's double line. I is connected to I, J is connected to J. These lines tell me that I is conserved in one line, J is conserved in another. And since it's a propagator, and two lines are separate lines, have to somehow draw that they are related to each other, therefore I draw the letter here. Now you see how I treat. This is a diffusor. And it looks like a diffusor, and it is a diffusor.
This vertical lines will come from the next border or from the same?
No, it's just the notation of this object. I just make it, well, if you like, if you don't like this vertical dash lines, you can make it just better this way. It's just anything with 4 ends. But anything other, these 4 ends are not equivalent. This connected to this one, that one connected to that. And it propagates only from this point to that point. It's like the same point in space, but different replicas. This is like another point in space, and also different replicas, but the first replica is the same as here, and the second replica is the same as here. So what we did, actually, the theory of this sigma model is exactly the effective theory that is written in terms of diffusons. Diffuson is the basic object which you can extract from this theory using the first order propagation.
And we got rid of our restriction for Q the moment when we chose T in this form, in exponential form.
This exponent here already resolves the restriction. Currently, well, since yeah, please.
There is something trivial how you get from action to this operator of fields.
How this action,
Yeah.
well, you should write this matrix as B explicitly with indices B, I, J, K, L, M, N, O, P, Q, and this trace is the sum of the indices.
Yes.
And then you will see that this is a quadratic expression. B is multiplied by some other B, and there is some matrix inside. It's a quadratic form.
Right.
And then you should invert the matrix of this quadratic form to get this matrix. It's actually pretty much diagonal, so it's easy to invert. But if
But should
you
I say that action is minimum to get this? So
wait.
I have
Action,
some expression of action, and okay, I do something with matrix, and
this thing here, the average,
okay.
is the integral over all things Q
Okay.
of B, I, J, K, L times the exponent of the action. This is the definition of what we call average.
Okay.
And then we put this action here, and it's a Gaussian integral.
It seems to me that the discussion of the Jacobian was promised.
Yeah. Unfortunately, I don't have time. So will be next. Will be tomorrow. What I may say at this point is that when you only do a Gaussian action, so the second order of Jacobian doesn't matter. Jacobian will be important if you expand it to some higher orders, and just to give you a flavor of this, if you expand to other higher orders, here W squared, Q and so on, and you put W in that form, and you expand the action, this gradient Q squared W up to higher powers of B, you will get already known Gaussian theory with this quadratic part plus parts of higher order, and these other terms will be the interaction forces. So this B field, it has a propagator, it's a free field, so this propagator defined by the Gaussian action. And then on top of this you have interaction, and the lowest order interaction will be something like trace B dagger B, B dagger B. Very cool, actually it's more complicated, something like this. And if you do this diagrammatic technique, where this is your propagator, this trace can be represented as like this. So you have matrix B, B dagger, B, B dagger, and you connect the second index of matrix B to the first index of the matrix B dagger. It's a matrix problem. then the second index of bit table with the first index of next. And then you connect last index back to the first index, and you multiply the matrices, and then you take the trace, you connect the last index here to the first index here, so you have this thing. They are all diffuse zones on all sides. And this is the interaction vertex. This thing tells you how the diffuse zones interact. And actually, if we do this compression, which we will do next time, you will see that this is exactly the Hikari modes we computed previously for the diagrams, which we will not see this discussed. Yeah?
Yeah, so will there be some correction from the Jacobian to this term?
Belongs to this one, to even height. Actually, we will never compute it because we will be smart and Jacobian will be simple one. I will explain next time how to do this. Well, so this is just one example. There are higher terms with b to the power 6, 8, 10, and whatever other numbers. And these are like interaction vertices, not of 2 diffuse zones, but of like 3-point interaction, 4-point interaction. So it's just to explain that this nonlinear sigma model is a non-trivial theory because it has interactions of all possible orders. It's not just 2-particle interaction, it's 3-particle, 4-particle, and so on. But they are all combined in such a single action, and all this complication is hidden in the fact that it really is on the closed space. So there is a very high degree of this symmetry within this model, and this symmetry we will always utilize to solve it in different cases. So we will not do the diagrammatic calculation like this. Never, but next time we will do it. So that's all for today. Are there any final questions?
Yes.
Yeah.
Just a very brief question on terminology. Why is it called sigma?
Honestly, there was something, historically, there was something called linear sigma model in the kind of physics around 50s or 60s. Then there was some complication of this, which was called non-linear sigma model. I've never seen it, no idea how it was like. But the people who invented this thing were they knew and they saw some analogy, that's why they call it non-linear sigma. And actually, I even asked them, and they even answered me, but since I never studied kind of physics, I don't know.